With some idea about symmetry elements and operations, we can now tackle the more directed objective of learning about molecular symmetry. So our learning goals for this are going to be to recognize the symmetry elements of molecules, including reflection planes, rotation axes, and inversion centers. We're also going to introduce at the end the Symmetry Otterbein website, which is a really great tool, a really great resource for you to use to learn about molecular symmetry. So, molecules as objects with symmetry. I mean, how do we do this? Molecules are kind of small. How can you tell? Well, we're going to treat molecules just as though they were solid geometric figures. So we're going to try to take each molecule and think of what is the solid geometric figure that captures the essence of the molecular shape and the distribution of the atoms. Positions of these atoms will then define as the molecule as an object, and we're going to treat that object as frozen. We're not going to be paying attention to the electrons in this case. We're really just focusing on where the nuclei are of the various atoms in a molecule. We're going to also ignore any vibrational motions and treat each molecule just as though it were stuck in place at its equilibrium shape. So the symmetry elements, we're only going to relate atoms of the same element. So if we have two different elements that would otherwise be in symmetrically related places, that destroys the possibility of symmetry. So what about reflection planes? We're going to consider ammonia as an example. Here's a picture of ammonia and what it looks like. It's a trigonal pyramidal molecule. So if we were to create like a little abstract statue of ammonia, we might start with a triangular base, which represents where the hydrogens sit. And then we would bring nitrogen down to connect to it, and it would create like a little tripod stand, if you will, a little trigonal pyramid that is the object that we want to find the symmetry of. This is the more abstract triangular pyramid. So what kinds of symmetry elements does it have? Well, it's got three planes that cut this triangular pyramid in half that are all running perpendicular to the hydrogen-hydrogen-hydrogen equilateral triangle, and they're shown above in the nitrogen molecule. These are the three reflection planes that we would find for ammonia. Now, about rotation axis, let's consider ethane as our example. So here's a picture of ethane, and you'll notice that it's in a staggered torsional conformation, so the hydrogens are not eclipsed with one another. If we were to draw a abstract figure that has the same shape, we might do it this way, where we draw first the carbon-carbon bond and then its extension to the hydrogens on each carbon atom. Each of those form an equilateral triangle, so the whole thing ends up looking, in an abstract sense, a little bit like this. So this object, this imaginary sculpture, if you will, would have the symmetry elements that we would expect to find in ethane. If we view down the top, it's like the Newman projection of ethane. We see perfectly staggered conformation of the various carbon-hydrogen bonds in ethane. So it's, I think, relatively easy to see that we must have a C3 axis along that line. If the hydrogens were eclipsed, it would, in fact, also be a C3 axis. But even though they're not eclipsed, we still have the C3 axis, a threefold symmetry of rotation about that. We also have some C2 axes of symmetry. So if you can imagine rotating this molecule by 180 degrees about that line, the one that's far away from us on the bottom would convert to the one that's closest to us on the top, and so forth. So all of those rotation axes are drawn here, and we see that there's a C3 axis down the bond axis of the carbon-carbon bond, and three C2 axes that are all perpendicular to it and meet at the center of the molecule. For inversion centers, let's consider the molecule benzene. Okay, so here is a depiction of benzene. It's a perfect hexagon. Is there an obvious geometric center? Well, of course there is. It's right here in the middle. And are the atoms related to one another by projection through that center? Remember, they all must have a twin that's related by inversion. So when we go from that carbon to the center, if we extend out an equal amount on the other side, we find another carbon. So yes, this in fact would be true for that one. For hydrogen, if we go through the center, we would go back out to that hydrogen. So we can do this for each of the carbons and each of the hydrogens in benzene. So yes, it does have inversion symmetry. Make a special note here that that inversion center does not have to be on an atom or on a bond in benzene. It can be in open space as long as there is an inversion center for the molecule. Now let's apply some of these to an example of 1,1-dichloroethylene. Here's the molecule. You can see that we have a carbon-carbon double bond. There are 2 chlorines on one side of that carbon-carbon double bond and 2 hydrogens on the other. So in this case, we have a C2 axis that runs down the heart of the molecule. So you can imagine if we flip that molecule, the top atoms will go to the bottom and so forth. The 2 carbon atoms are on the axis, so they don't move at all. This also means we have a reflection plane that goes through there, and those 2 atoms, the 2 chlorines, are related to one another by reflection, as are the 2 hydrogens related to one another by reflection. The carbon atoms are in the plane, so they are automatically related by the reflection. There's also a plane that contains the whole molecule, and that is also a symmetry element. So all of the atoms now are lying in the plane, and they're all related by reflection through that plane. Here is a picture that shows us all 3 of those symmetry elements, the 2 reflection planes and the C2 axis, so you can see how they're all related to one another. Note that this rotation axis is actually the intersection of the 2 reflection planes. When you have multiple reflection planes like this that intersect, their intersection set will almost always be a rotation axis of symmetry. You can learn a lot more about molecular symmetry if you use this website, and I really urge you to do so. It is featured in the lesson that I've put online, and it's a great site for learning about symmetry elements and how they relate to molecules. This is what it looks like when you get there. I should note that Otterbein is a private university in Central Ohio, and one of their chemistry professors there got a special grant to put this together, and he did a beautiful job of showing you how symmetry and molecules work together.